Today we will prove that the function phi is multiplicative, and for that we are going to need this lemma, which states that for any three integers a, b and c, a and bc are relatively prime, that is their GCD is 1 if and only if a and b are relatively prime and a and c are relatively prime. So let's first prove the lemma and then we will turn to the proof that phi is multiplicative. The proof starts like this. Because this is an if and only if statement, so we have to prove two implications. This implies these two things and these two things implying this. So we first assume this, that let the GCD of A and BC be equal to 1. Now let us first show that this GCD is 1. We give it a name also so that we can write it more easily. We are calling it D. Now we need to prove that D is 1. And then afterwards we will also say how this is then 1. Now since D is the GCD of A and B, it's after all a common divisor of A and B, it will divide both A as well as B. So that's where we start the next sentence. Since D divides A and D divides B, so we have D dividing A and D dividing BC also. If D divides B, automatically D divides BC. But then D becomes a common divisor of A and BC. And so D will be less than or equal to their greatest common divisor, because this is just some common divisor and this is the greatest common divisor, which however is 1. So we are getting the fact that D is less than or equal to 1, but D itself being a GCD is by definition positive, so D is also greater than or equal to 1, and that's how D is equal to 1. So that means we have shown that this GCD is 1. Similarly, this other one is also 1, so that is 1/2 of the proof. Now we will prove the converse. Conversely, let the GCD of A and B be 1 and the GCD of A and C also be 1. And this time let's give this GCD a name. Let's call it D1. Our aim is to now prove that D1 is also equal to 1. But contrary to the claim, suppose that D1 is greater than 1. Then by the fundamental theorem of arithmetic, D1 will have some prime divisor P. Now because D1 is the GCD of A and BC, D1 divides A and D1 divides BC, and because of this and the fact that P divides D1, so now P will also divide A as well as BC. But keep in mind that P is a prime. So by a corollary to Euclid's lemma, this is what we get. Because P is dividing BC and P is the prime, so P has to divide at least one of them. Either P divides B or P divides C or both. Suppose P divides B. Then since P also divides A, P becomes a common divisor of A and B, and as such it will be less than or equal to their greatest common divisor, which however is 1, because that's the part of the hypothesis. This however is not possible because P is the prime. How can it be less than or equal to 1? So you have got a contradiction here. A similar contradiction arises if you assume that P divides C. That is because the GCD of A and C is also 1. So that means our supposition must be false. So D1 has to be equal to 1. So this completes the proof. And then we have our main theorem, theorem 7.2, which states just that the function phi is a multiplicative function. We start the proof by considering two co-prime positive integers m and n. Co-prime means relatively prime, because it's easier to write co-prime, so I am using this. Both co-prime and relatively prime mean that their GCD is 1. Be two such integers means be any two such integers. Okay. We want to of course show that the phi value of mn is equal to the phi value of m times the phi value of n, because that's what being multiplicative means. Now among the infinitely many different possibilities for m and n, this is also a possibility that n is something, some integer, and m is 1. Let's see what the case is. In this case, what will be phi of mn? phi of mn will just be phi of n because mn is equal to n. That's because m is 1. But you can write phi of n as 1 times phi of n. And you know from our previous discussion that 1 is equal to phi of 1. And that comes from the definition itself. But phi of 1 is phi of m. So what you are trying to prove here is true in this case. Similarly, the formula is true if n is equal to 1. That means if either m is 1 or n is 1 or both are 1, we are done. And that is why we are now assuming that both m and n are greater than 1. Now next, consider the following arrangement of these integers, all the positive integers starting from 1 and ending with mn. In m columns of n integers each. These are the m columns. First column, second column I did not show because I don't have that much space. This is the general earth column and this is the last column. Each column has n entries in it. And you can try to understand this array of numbers like this. If you go in this fashion, you just increase the integers one by one. After 1, you will have 2 in the next column as the topmost entry of the second column, then 3, then 4, like that you reach m, and then m plus 1, m plus 2, like that it goes. In the last row, because these are rows, things go like this: n minus 1 times m plus 1. Then the next one, which you don't see here, will be n minus 1 times m plus 2. Okay, and for the earth one, it is that thing plus r, and finally this one, nm. n minus 1 times m plus m, so that n that becomes nn. In fact, that's how you get these other entries in this last column also. Now we know that phi of mn is the number of integers in this array that are co-prime to mn by definition, of course. And by the previous lemma, that number also equals the number of integers in this array that are co-prime to both m and n simultaneously. GCD of a and bc is 1 if and only if GCD of a and b is 1 and GCD of a and c is 1. In place of a, you think of the desired integers from this array, and in place of b and c, you think of respectively m and n and apply the previous lemma. So that means that we have to find the total number of integers in this array that are simultaneously co-prime to m and n. Now this is one crucial observation. Note that since the GCD of qm plus r and m is equal to the GCD of r and m, the numbers in the earth column, which look like this, which have this form, are co-prime to m if and only if r itself is co-prime to m. This is 1 if and only if this is 1. So what does that mean? It means that if r is co-prime to m, then all the numbers in this column are co-prime to m, otherwise not. Otherwise none of them is co-prime to m. If you are thinking about how this is equal to this, you recall what you did when proving the Euclidean algorithm. I mean that algorithm which lets you calculate GCD in an effective way, where you again and again divide. First you divide one of the numbers by the other, then you divide the divisor by the remainder, that thing. There, that algorithm itself rests on this observation. And because of this, only phi of m columns contain integers that are co-prime to m. And all integers in each such column will be co-prime to m. For example, you consider the first column. Because 1 is co-prime to m, the GCD of 1 and m obviously is 1. So all these integers are also co-prime to m. So in your search for finding those integers that are co-prime to simultaneously m and n, you have found this fact at least, that among all these columns, only phi of m columns have integers which are co-prime to m. If you look at the topmost members of those columns, there itself you will know which columns have those integers that are coprime to m. The top member has to be coprime to m. Like this one, there will be other options. This last column, for example, does not have integers which are coprime to m, because the GCD of m and m is m itself, which is not 1. Why? Because you remember, m has been assumed to be greater than 1, n is also greater than 1, and once you locate such a column, in that column all integers are coprime to n. Okay, but what about n? Now among these integers which are coprime to m, you also have to find those specifically that are simultaneously coprime to n. Now if we can show that each such column, what type of column? Namely those columns where all the integers are coprime to n, that each such column has exactly phi of n integers that are simultaneously coprime to n, then we are done, because then the total number of integers in this array which are simultaneously coprime to m and n will be phi of m times phi of n. That's what we want to show, right? Now we isolate the integers in the rth column and write them like this. The numbers in the rth column are r, m plus r, 2m plus r. You can see the pattern. And the last one is n minus 1 times m plus r. We now want to know what the status of these integers is modulo n. And to know that, we are supposing something here, that km plus r is congruent to jm plus r modulo n, which just means that we have picked two members from this list and we have assumed that they are congruent to each other modulo n, not m, okay, n. And to also indicate that we have chosen two distinct members which actually depend on what? This number. M and R are fixed. In all these numbers, m is present, r is also present. You don't see m in the first one because the coefficient of m is 0, but still it's present in a sense. So the two things that we have to choose are those coefficients which we are calling k and j. K and j lie in this range between 0 and n minus 1 inclusive, but they are not equal. Is it possible? Let's see. Now simplifying this congruence, you immediately get this. Km is congruent to Jm mod n. Then, if this is true, cancelling r from both sides. We can do this by one of the properties of congruences. But additionally, we also know that m and n are coprime. So you can cancel this m also, obtaining this congruence that k is congruent to j modulo n. But this is impossible because of these inequalities. Why? Well, what does the middle inequality tell you? It tells you that j minus k is a positive integer. But at the same time, j minus k is of course not exceeding j, it's in fact less than or equal to j, because k is non-negative. And j itself is not exceeding n minus 1. So j minus k is a positive integer less than or equal to n minus 1, that means it is less than n. This congruence, however, tells you that n divides j minus k. That is not possible. And that is why this supposition is wrong. So in that list means among these integers, if you choose two distinct integers, they are not congruent to each other modulo n. So all these integers are mutually incongruent modulo n. So these numbers, that is these numbers, are mutually incongruent modulo n. But how many numbers are present in this list? N numbers. If you start counting from this second one, because here the coefficient of m is 1, by the time you reach this last number, you have counted n minus 1 numbers. You include that first one also, you get n numbers in this list. Now, you have got n integers which are mutually incongruent and the modulus is n. So that means these numbers must be congruent modulo n to these numbers. That is the largest number of integers which can be mutually incongruent when the modulus is n in some order. In some order means you may have to rearrange these integers so that after rearranging them, the first element will be congruent to 0 mod n, the second one will be congruent to 1 mod n in that sense. But if s and t are two integers congruent to each other modulo n, then s and n are coprime if and only if t and n are coprime. So what does it all mean? It means this. So the number of integers among these, that means among the integers in the rth column that are coprime to n is equal to the number of integers among this that are coprime to n among the first n minus 1 non-negative integers, because these are congruent to this modulo n in some order. And this number is phi of n. Do not be confused about having this 0 here, because your n is greater than 1 just like m, so you are not losing anything when you are not considering n, and when your aim is to find those integers that are less than or equal to n and relatively prime to n. So neglecting n, you are not losing anything. Also bringing in 0, you are not gaining anything, because 0 anyway is not relatively prime to n because n is greater than 1. All those integers that are coprime to n which you are seeking among these numbers are contained in this part, and that is present, and that number is phi of n. So this is what you wanted to show, right? If r is relatively prime to m, then all the numbers in this column will be relatively prime to m. But among them, exactly phi of n are simultaneously relatively prime or coprime to n. How many such columns are there where the numbers are relatively prime to n? Phi of n columns. And in each column, this many members are also simultaneously relatively prime to n. So the total number of numbers in this array that are coprime to m and n is phi of m times phi of n, which however by definition is phi of mn. So that's how you have that equation, and here the proof ends. And let me end the video itself here. In the next number theory video next week, we are going to see consequences of this fact that phi is multiplicative.